we've talked about charge, let's go ahead and think about force. So remember, force is in newtons, and to keep things in perspective, we've done a lot of work with gravity as a force, but gravity, compared to other forces, is pretty weak. So our formula for electric force is actually very similar to the formula for gravitation. So we will have K being our constant for electric force times the absolute value of our first charge times the absolute value of our second charge divided by r squared, where r is the distance between them, and that is going to give us our force due to the charges. Now, I would argue that the absolute value portion of this formula is not necessary, because if you understand what's happening with the charges, you don't ever have to actually put that in your calculator or anything like that. Just know that like charges are going to repel, and different charges, opposite charges, are going to attract. So basically, if when you do the force, you get a negative answer, that means that force is going to be attractive, and if you get a positive answer, that force is going to be repulsive. Okay, so what is the force of attraction between a 400 microcoulomb charge and a negative 500 microcoulomb charge if they are separated by 2 meters? That's fairly far apart. Okay, but first of all, 400 microcoulombs. That's going to be 400 times 10 to the negative 6 coulomb, and this is going to be negative 500 times 10 to the negative 6 coulomb, because 1 microcoulomb equals 10 to the negative 6 coulombs. Okay, so let's use our formula. Force is going to equal K. Now our K is right here. I would definitely program this into the calculator so you don't have to type it all the time. But it's going to be 8.99 times 10 to the 9th times, and we're going to have 400 times 10 to the negative 6 coulomb times negative 500 10 to the negative 6 all over r squared. So that is going to be 2. That is going to be 2 squared. Okay, so I'm going to put that all into the calculator, and we'll get our answer. And I'm actually not even bothering putting in the absolute value symbols. Those ultimately are not going to matter. We just need to understand our answer. So when I type it in, I get negative 449.5. And after rounding, that's going to give me 400, negative 450. But let's analyze. So since my answer is negative and these charges are opposite, that's attractive. So our force is 450 newtons. Attractive. These are going to pull towards each other. Okay? And if the distance between them doubled, so if instead of 2, we had 4, so everything's going to be the same, except now, at the bottom, I'm going to have 4 squared instead of 2 squared. So it's not that that force is going to be halved, but it's going to be, I don't know how to say this, it's going to be the reverse of quadrupled. So that we'll have a 16 down there instead. So let's go ahead. Well, put that in. We'll have K times our 400 microcoulombs and times our negative 500 microcoulombs. Now you do need to switch the microcoulombs to coulombs in order for the force formula to work, at least correctly. And we get a force of negative 112 newtons. Now, not negative though, right? That tells us it's attractive. That's all that sign means. So our answer should never actually be negative. It's just a matter that negative or positive is going to tell us whether it's attractive or repulsive. So this is attractive since it is negative. If it was a positive answer at the end, it would be a repulsive force. Okay, at what distance between 12 microcoulombs and 32 microcoulombs would we get a force equal to 2? So here's our formula, and we're just going to plug in everything that we know. We're looking for R. R is our distance between them. So we know that we're going to have 2 newtons. And K is 8.99 times 10 to the 9th. I'll make sure I put that right. Oh, yeah, okay. I just want to make sure I wrote that right over there. Times. And Q1 is now 12 microcoulombs. That's going to be 12 times 10 to the negative 6. Now, technically, this isn't correct scientific notation, but ultimately, because I'm multiplying it out anyway, doesn't matter. Don't need to worry about it. So these are in coulombs now, and we're solving for R squared. So this would be over 1. I'm going to multiply out all of the numerator, and then I'll cross multiply. So let me go ahead and multiply out that numerator, and you could do a lot of this all at once. It's negative 6. So in the numerator, I have 3.45216. I'll save the final rounding to later, so I'm going to cross multiply. And when I cross multiply, I'm going to get 2R squared equals 3.45216. We'll divide by 2. And then we're going to square root. So we're going to square root these. And we get R is 1.31 meters. This is meters. So earlier we were taught when we were doing like charge, we did all our masses and things in kilograms. There is a reason to do kilograms because when we talk about force, force is, in kilograms and meters and seconds. So just get all our units agreeing and life is a little bit easier. Okay, so a negative 7 times 10 to the negative 6 charge experiences a 1.5 Newton repulsive force from another charge that's 1.5 meters away. So this is our R. This is one of our Q's. It doesn't matter which one. And this is our force. So if we start plugging into our formula, I won't write the formula again. So we'll have 1.5. And I'll go ahead. I mean, I could keep that sign. It doesn't really matter that much. But it is a repulsive force, so I know since it's a repulsive force, the other thing should be negative as well. So this is going to be Q for our charge that we're looking for. Why did I put 1.5? Oh, it is 1.5. Those are the same. All right, so 1.5 squared over here. So I'm going to multiply both sides by that 1.5 squared. So I basically get 1.5 cubed. So on the one side. And that's going to lead us to 3.375 equals negative 7 times 10 to the negative 6 Q. So we'll divide both sides by negative 7 times 10 to the negative 6. And by keeping that sign actually is going to get me the correct Q. Boy, this Q is rather large compared to that one. I'm probably, in setting this up, I probably wanted less force than that right there, or either more distance, something like that. So -4, 8, 2, 1, 4, 2 coulombs. Holy. Ouch. Stay away from that. That's huge. A coulomb is pretty large, so that we have this large of a charge, pretty scary. So weird problem right there. Okay. The attractive force between two charges is 2.4 newtons, and the charges are separated by 1.8 meters. If one charge is doubled in magnitude of the other, what are the magnitudes of their charges? So I'm going to let Q equal the first charge, and since the other charge is double, 2Q equal the second charge. Okay, and here's our formula. So we'll start plugging in. We have 2.4 newtons. We have our, oh, I just realized what went wrong over here. I forgot K. So let's go ahead and fix that. So let's see what changes right here. Let me get the red ink. Mr. Kane made a big mistake. Okay, so we need our K. So this is 8.99 times 10 to the 9th. So maybe this problem wasn't so weird after all. So we cleared by multiplying by that. So we do get the 3.375, but we have this 8.99 times 10 to the 9th and -7.0 times 10 to the -6, then our Q. So I'm going to multiply these two numbers together and then divide into the other side. So I'm not going to do all of that or show all of that anyway, because we already did this problem. I just messed it up. Okay, that's a lot more reasonable. So our Q in the end here should have been -5.36 times 10 to the -5th coulomb. That is the right answer. That is the wrong answer. This was wrong because I forgot K. That's why you should write your formulas down. See, I was being lazy. You should have wrote down my formula. Okay. All right, going on. So remember K this time. 8.99 times 10. And that's our constant here to the 9th. So our first charge is Q, and our second charge we said is 2Q. All over the distance between them is 1.8 squared. Okay, so I'm going to, again, multiply both sides by that 1.8 squared. And I mean, you could square it first before you clear it. And here's what we get. All that times, now, Q times 2Q is 2Q squared. So 2Q squared. All right, so I'm going to multiply these two things and then divide them. So I'm going to divide both sides by 8.99 times 10 to the 9th times 2. You may want to just multiply that out before dividing. Actually, I strongly encourage you to do that, which is actually, as I'm doing this, that's exactly what I'm doing. But in the interest right here, I get Q squared equals 4.325 times 10 to the -10th. We'll square root that. And when we square root it, our Q is 2.0796, which means 2Q times 10 to the negative fifth, which means 2Q is 4.159 times 10 to the negative fifth coulombs. Okay, good. So over a microcoulomb there. Okay. Let's go on. All right, so now suppose a negative 4 microcoulomb charge is at the origin of a coordinate plane and a proton is slowly moved up the negative y-axis. At what distance is the force acting on it exactly opposite its weight? So we picture this situation. Here's our coordinate axis, and here's our charge, negative 0.4 microcoulomb is right here at the origin. And we have some sort of proton right here. And we're slowly moving it up. And we're wondering, when is this distance going to be in balance with gravity? Now, that would mean the force of attraction towards this negatively charged area equals the force down. So on this proton, if you picture this proton, we're going to have a force up due to charge, and we're going to have a force down due to gravity. But here's the disclaimer with this problem and the reality of this problem. Gravity is by far a weaker force than electrostatic force. So when we're talking about like gravity acting on these particles, kind of dodgy. But let's just go with it anyway. So let's change this to coulombs. So this is negative 0.4. I'm not going to bother getting this into correct scientific notation. There's our coulombs. We need to know this force due to gravity. And the force due to gravity is mass times acceleration. So the mass, this is a proton, and the mass of a proton is up here. And that needs to be in kilograms, and it is. And our acceleration, 9.81, downward. Okay, so let's go ahead and find out what that is. And we get negative 1.641 times 10 to the negative 26 newtons. So, what this question is asking is, at what is this distance right here where this force, this electric force, this force due to charge, is going to balance out with the force down. So we have the force down. So our force due to the charges is going to be K times the first charge times the second charge divided by the distance squared. So we know that this is our force. Now we aren't going to do the negative. We're going to ignore that piece. Our K is 8.99 times 10 to the ninth. And our charge is negative 0.4 times 10 to the negative 6, coulombs. Now, what's the charge on a proton? Right here. So 1.6 times 10 to the negative 19 coulomb, all over r squared. So if I cross multiply, what I'm ultimately going to get is r squared equals 8.99 times 10 to the ninth times negative 0.4 times 10 to the negative 6 times 1.6 times 10 to the negative 19 Now these are opposite, so I do expect opposite charges to attract. All would be divided by this number right here, 1.641 times 10 to the negative 26. And then at the end, R, I'm not going to write all of this again, is going to be the square root of that answer. So I'm going to do most of that simultaneously. Let's do the first part, 8.99 times 10 to the 9th times negative 0.4. Now, when I do that square root, I'm actually not going to want that negative right there. So I'm actually just going to take it out right here, times 10 to the negative 6 times 1.6 times 10 to the negative 19th. Just remember, those signs are letting us know whether we're attractive or repulsive. So this should be an attractive force. Okay, so I'm going to get inside here 3.5056 times 10 to the 10th, and then I'm going to square root that. Okay, so I get, did I forget something? I get R equals 1.8723 meters. All right. Why can it be so distant? Let's see, that's over what? Over several hundred kilometers. So very distant. Why is that the case? Well, because the force due to charge is just so much bigger than gravity. And remember how I prefaced this problem. Is that, while gravity does act on all masses, when we're talking about like the small, is really negligible and kind of a dodgy situation. If we wanted to make this more realistic, instead of doing, this microcoulomb, if we made it a nanocoulomb, this problem would tend to work out much better, and we would have this distance being much smaller. And what is a nanocoulomb? Well, a nanocoulomb equals 10 to the negative 9th coulombs, which moves this all down significantly. In any case, that is how we will be applying force to charges.